does that look right?
Yes, that is looking great.
Okay, good. Awesome. Thanks, Drew, for getting us started. Yeah, so as it said, I'm Maddie Smith. I'm a postdoc at the Polar Science Center at the University of Washington Applied Physics Lab. And yeah, so I mean, sea ice is such an interesting part of the ocean and climate system. You can see that in this video. It's also really beautiful. It sits really at the very upper part of the ocean. And so it alters the exchanges across the air-ocean interface, including notably the transfer of heat or thermal energy and the momentum. So in the next few minutes, I'm going to highlight a few recent results from my involvement in ONR's DRIs, especially the Sea State campaign that I was a part of in 2015, which has given largely insight into changes in the marginal ice zone. And then also the recent Mosaic campaign gives us unique insight into the processes in the central Arctic's pack ice in terms of these exchanges. So the work that I'm highlighting is a result of collaboration with many people, especially those listed here, but not limited, many more involved. So the air-sea exchange of thermal and mechanical energy are closely connected in the Arctic because there is often really strong stratification from fresher water near the surface. So while globally mixed layers are often hundreds of meters deep, in the Arctic, the mixed layers tend to be much shallower. And this figure shows all of the mixed layer observations from Arctic in the summer when the mixed layers are typically shallowest. And you can see that summer mixed layers are often on the scale of 10 to 20 meters, or even less, down to 5 to 10 in some areas. An example of the impact of this is in the Western Arctic, this can lead to the trapping of solar heat during the summer near the surface in a layer below the mixed layer referred to as the near surface temperature maximum. And you can see an example in this profile from the Beaufort Sea in 2015, where you can see this peak in temperature from 25 to 35 meters below the surface. Even more so in areas of high ice concentration during the summer, like in the pack ice, we can see strong heat accumulation in just the upper meter or so, where there's significantly fresher water from ice melt. So you can see that in these example profiles from Sheba in the summer of '98 in the Western Arctic. So the point here is that these strongly stratified upper ocean layers on different scales lead to impacts not only in how the thermal energy is exchanged, but also can impact how mechanical energy is transferred from the atmosphere via wind and ice drift to the ocean below. The Office of Naval Research has funded a number of initiatives over recent years focused on understanding upper ocean and atmosphere interactions in various ways, which many of you are likely familiar with to varying degrees. Here I'm going to talk a little bit about some results from Sea State, which I was involved in for my PhD work. And it focused on answering the question, what are the effects of storms and waves when the ice begins to regrow and advance southward in the fall? So the field experiment took place in 2015 in the Alaskan Arctic and the Beaufort Sea, which you can see in the map on the right here. And it used a combination of ship-based and autonomous platforms to understand air, ice, ocean interactions. You can see a lot of the different instrumentation that we used in the schematic on the left. And so the goal of all of this was to understand the evolution during fall freeze up in this area where there's often warm water remnant into the fall, and that plays a large role in the ice advance and progression. So the presence of fall storms with large waves and strong winds can drive strong energy transfer, potentially delaying the ice advance here. A really nice contrast to this is provided by the Mosaic expedition with US participation funded primarily by NSF. As many of you probably know, Mosaic was a year-long drift expedition and it ended in September of 2020. And it was all based around the polar stern, which was the German icebreaker that was frozen into the ice and was also made up of presence on the ice with camps and instrumentation for the entire year. And the science involved researchers focusing on nearly all components of the Arctic system, from the atmosphere, ocean, and sea ice, as well as the ecosystem, to get an integrated understanding of changes over the full annual cycle. I was on the summer leg, focused on processes and feedbacks driving the accumulation of heat in the ocean and melting of ice from this spring to summer transition. So in addition to being in a different part of the Arctic than Sea State, and the other ONR initiatives, this campaign also necessarily focused on the pack ice more in the interior, where the air-sea interactions are fundamentally different than in the marginal ice zone. During Mosaic, part of our work was to address where does the freshwater in the upper ocean come from to result in this strong stratification that we've seen previously that you saw on one of those first slides. So during the Arctic summer, snow and ice melt provides a significant source of freshwater. Some of this accumulates into melt ponds, which you can see on the surface of the ice in this photo, which can then drain from the ice to the ocean, either below, potentially accumulating in under ice melt ponds, or to the ice surrounding, or to the ocean surrounding the ice, to the leads. So we can end up with this really strong stratification on the order 1 meter, so much less than the mixed layer depths, from this accumulating under and between ice flows. So looking up towards the ice through a hole in the mosaic flow, we can actually visually see the kinds of freshwater layers we end up with on the order of about 0.5 meter thick under the ice on the surface. And this freshwater is forming a pretty distinct layer with the salty water below. And this transition, the halocline, is particularly evident here because of this high concentration of biological material trapped. So you can kind of see that in this photo. The accumulation of this fresh layer obviously has impacts for the ecosystem, which you can see, as well as the sea ice mass balance, but also the exchange of energy between the atmosphere and the ocean, as it's sort of acting like a barrier here. So we observed the accumulation and also evolution of a fresh warm layer during Mosaic throughout the month of July. And this plot shows just the salinity averaged over the upper 7 meters. This was measured from a castaway in a kayak. So this is measurements on 7 different days, including about 5 to 10 profiles averaged in each. And we can see a low salinity layer in all of these. We can zoom in to get a little higher resolution near the surface. So these plots show temperature above freezing on the left and salinity on the right, made with a different instrument that allowed us to get higher resolution in the upper 1.5 meters here. So on just the 4 days that I'm showing, we can see some variability in the heat in these average profiles. And while we see some periods where heat is building up, as in the shaded region, it's also not clear that it's clear that it's not a simple story of just heat building up. And part of that is because there's energy transfer from the wind and ice motion throughout the summer that can sometimes mix down this heat and meltwater, as well as the strong stratification is constraining the energy transfer to some degree to this layer. So in some ways, the evolution of the upper ocean over time is a result of the balance of the thermal energy input and the mechanical energy inputs to the upper ocean. So these types of layers that we observed on Mosaic might be expected to be seen most commonly in the pack ice during the summer, where the energy inputs from the wind are fairly low, although observations of sufficient scale to do so have been historically rare. But the area of the ice of the Arctic that is this pack ice in the summer is decreasing, and the portion of MIZ relatively is increasing. So with the loss of sea ice in the Arctic, the fetch for waves to grow is increasing. And we can see that in these maps of coverage from 1979 and 2012, where, for example, we can see there's this much larger area of open water in 2012. So as we showed in a recent paper, this is the result of this is that the wave heights in this area on the top plot have gotten bigger since the 90s, even as the wind speeds are staying approximately constant, which you can see on the bottom. So the waves in the Arctic are increasing because this ice-covered area is decreasing. And these waves enhance the air-sea fluxes. So though the maps show the ice edge as a distinct clean line, this is often not the case. And we actually have regions of partial ice cover in the marginal ice zone where there are still significant waves. And so the ice at the surface is drastically changing the air-sea interactions from the open ocean, but conversely, the waves are also enhancing the fluxes from what we'd expect to see in the pack ice, like on Mosaic. So we can just see an example of that here, where we have waves in a marginal ice zone with actually pancake ice on the surface. And you can see that the waves are causing significant motion of the ice at the surface, but the ice is also attenuating the high frequency waves and creating a smoother wave field. So that ice is significantly changing the momentum transfer from the atmosphere to the ocean. The momentum drives the near surface turbulence, which is important also to transfer of other quantities, including heat and gases. During sea state and other ONR experiments, we made measurements with buoys in the marginal ice zone and during ice growth to address the question of how ice alters the mixing and turbulence near the surface. So the turbulent mixing is elevated in the upper few meters above background levels due to the input of wind energy through the waves. So here it's understood that the waves are providing the roughness for wind stress to transfer momentum into the ocean. And in particular, studies have shown that the wind stress, tau, is input at a rate which we can call C sub E that's related to the speed of the short waves. So conceptually, that's the roughness of the surface. So locally, the wind input is imbalanced with the dissipation rate of turbulent kinetic energy. But we want to understand more about how this has changed in sea ice. And Zippel and Thompson showed with observations from these buoys that even a small fraction of sea ice damps the short waves on the surface. And this in turn suppresses the turbulence from from the transfer of energy from the wind into the ocean through the reduction of this term C sub E. So in this example here, the waves are significantly reduced from open water to about 50% ice cover in blue. And we see a corresponding decrease in the dissipation rate profile from the surface downwards. Building on that, we found that new ice covers also reduce the C sub E in a similar way as a function of the ice thickness and concentration in addition to the wave height. So overall, the momentum input is reduced in ice by an amount that is a function of the ice conditions and related to the changes in wave size and roughness. So what are the consequences of this energy exchange and this increasing energy exchange in the Arctic? One result is that the mixing associated with winds and waves can then interact with heat reservoirs below the surface to entrain heat and melt ice. Quickly, I just want to mention that we saw an example of this on sea state in 2015, where there were strong winds and large waves, which we can see in this time series. The black is the winds getting up to 18 meters per second, and waves in yellow got up to a significant wave height of about 5 meters. And what I particularly want to show you is that over time, coincident with this, we saw from underway CTD profiles, small changes in the upper ocean temperature. So here, these example temperature profiles show that we initially had this near surface temperature maximum about 22 meters below the surface. And that becomes deeper with mixing and loss of heat above. So that the heat that was lost is represented by the red shaded area in these overlaid profiles on the right. And that coincided with observations of pancake ice loss on the surface of about 5 centimeters total. We didn't see this change as clearly in areas of newly formed ice where waves weren't present. And this indicated that the energy input from waves has meaningful consequences for the ocean heat and the sea ice. And so the stratification in terms of heat and salinity not only has consequences for the ice, but also the fate of energy across the interface. So as a general conclusion, the air-sea exchanges of energy, heat, and momentum are changing and increasing in the Arctic with declining sea ice cover. And these are largely all connected. But I also want to end by offering a few quick ideas by what I see as key areas for continued work as a result of these projects. And the first is improving and expanding observations of fine-scale stratification and sea surface salinity. As the observations from Mosaic show, this really does go beyond just the mixed layer depth, those types of observations that we can see traditionally from profilers to really fine-scale just near the surface. Because this stratification is impacting the heat and momentum exchange, as well as gas fluxes, et cetera. Additionally, waves are becoming an increasingly important part of the Arctic system. They have impacts on the near surface stratification and direct effects on the exchange of momentum and thus turbulence. So there are efforts underway to couple wave models with other model components in the Arctic, or that are part of the Arctic, the sea ice and the ocean. And we should also continue to support these model developments with increased observations. And I want to thank again, ONR and NSF for funding research in these areas. And I'd be happy to answer questions if there are any.
Thank you, Maddie. That was a fantastic presentation. I think in interest of time, we're going to save questions until the end of the second one. If folks are worried that they're going to forget their question, you can go ahead and enter it into the chat, and I will make sure to read those out by the end. But again, thank you, Maddie. That was a great presentation. So up next is Ian Renfrew. I believe he is here. Ian, hello. Ian is a professor at the University of East Anglia. And Ian, whenever you are ready to share your presentation, we could get that started.
Okay, thanks very much, Drew. I will click share screen. Okay. Can you see? Oh, what could? I'll just go into presentation mode.
Yeah.
Is that okay? Can you see the full screen, or can you see?
Yes, we can see it in presentation mode.
Brilliant. Okay. I've got two screens and I can see both, so I always get confused about which one my lovely audience can see. Anyway, okay. Well, thanks very much for the invitation. I should first of all say that I actually wasn't invited to do this. I'm talking on behalf of Andy Elvidge, my colleague here at UEA, who was asked to do it, but he's on holiday, so he twisted my arm, and I'm stepping in. So we're looking really at the air side fluxes between the surface, so the ice ocean mixture, and the atmosphere. And I'm going to be talking about both momentum and also heat and moisture. So I've kind of tried to split it into two parts here. And this is work funded by NERC and often led by the University of East Anglia. So you can see in this schematic here, this is the marginal ice zone. The black is indicating low-level winds, and the curvy arrows are indicating the elevated turbulence that we get in the marginal ice zone. And so you can imagine during this situation of cold air outbreak, sort of cold air flowing from the ice pack over the marginal ice zone and further downwind, we're getting a deceleration of the mean wind as the atmosphere interacts with the sort of ridges and melt ponds and other drag features within the marginal ice zone. So how do you cope with that in a numerical model? We'll be trying to address that sort of question in today's talk. So you need to have a drag coefficient, which is indicated here by CDN10. And that drag coefficient is a way of parameterizing the exchange of momentum between the atmosphere and the surface, or in other words, the drag that the surface imparts on the atmosphere. And in the marginal ice zone, you typically have a component due to water. So C, 1 times A, so A is the area of sea ice. So 1 minus A times the drag coefficient for water, plus A times the drag coefficient for ice, plus this form drag element, which is essentially due to the winds blowing against vertical faces. And the simplest way of parameterizing this drag, this form component, is some sort of function of ice fraction. And if you want to know a lot of details about this, then work by Christoph Lübkes, for example, discusses this in some detail. So whenever you have some sort of parameterization like this, you need observations to tune your parameterization, to develop your parameterization. And we've had a couple of field campaigns in the last few years, Acacia in 2013, and then this IGP campaign in 2018, where we've flown over the marginal ice zone quite a bit with a Twin Otter aircraft, instrumented Twin Otter, and measured heat and moisture exchange using the eddy covariance methodology. And when we published the Acacia data set in 2016, this doubled the amount of data over the marginal ice zone that was previously available. So in other words, this sort of data is quite difficult to get because it's difficult to get observing platforms into the marginal ice zone, and so you're limited to sort of aircraft and bold research vessels. There we go. So I'm going to cut to the chase with the results from that Acacia field campaign. And you can see the graph on the left here. What I'm showing is the exchange coefficient for drag, the momentum coefficient, drag coefficient here as a function of ice fraction. And our observations are the box and whiskers plots here, so the black bars. And you can see that there's an increase in drag coefficient across the marginal ice zone. So the largest drag coefficients are around 0.6 or 0.8 ice fraction. And then there's a lower ice fraction over 100% sea ice, and then lower also over open water. And this sort of functional form matched reasonably well with the theoretical based parameterizations from, for example, Christoph Lübke's group and Ed Andreas and others. So this black line here and the gray line here are two different tunings of the Lübke's parameterization based on our observations. And they're shown in both the left panel here, and they're also shown in the right panel. And the right panel, so they're the same black and gray lines. And the right panel is from a literature survey that I did at the time. So this is back in 2015, 2016, of how drag was parameterized in a range of NWP, so weather and climate prediction models. And you can see that a couple of the models do have this peak in exchange coefficient, in drag coefficient over the marginal ice zone. So for example, the East Anglia forecast model in cycle 41, which was released in 2015. In fact, we consulted with them when they were doing this work. They went from having a linear interpolation between open water and marginal and 100% sea ice to having this peak over the marginal ice zone, which was consistent with observations. But other modeling centers such as the Met Office and the climate CCSM, the US climate model, just didn't have this peak. So how important was that? Well, we decided to do some model sensitivity experiments, and this is using an atmosphere only model. It's using the Met Office unified model, which is their model used for operational weather forecasting, and it's also key part of their climate model, so part of HADGEM3, for example, and that family of climate models. And we did 3 different atmospheric experiments. We did a rough experiment with a large amount of surface roughness over the marginal ice zone, and that's this blue dashed line here. And the reason we used that was because that was the operational scheme up until September 8, 2018. And it had a fairly unrealistic drag exchange coefficient, actually, but which they kind of knew about for a while, but didn't do anything about. And then we had our new scheme, which is this L12E16 scheme, the black line here, and then a smooth scheme, which a relatively low roughness length, which was used in some of their climate model configurations. And we ran 2 types of sensitivity experiment. We ran one on a local domain, just of the European Arctic, where we had an observational data set. And the second was a global model domain. And for the local domain, we sort of ran 2 weeks of daily forecast experiments. And for the global domain, we ran a sort of basket of case studies, sort of standard test suite that the Met Office had. So how did the results pan out? Well, these are some results from the regional simulations. And these are just scatter plots of observations versus model output from the rough, from the new scheme, and from the smooth settings. And you can see that, good news, the new parameterization scheme validates better. This is scatter plots for temperature. And down in the table here, you can see I've got some data for temperature and wind. And you can see that the new scheme, the L12E16 scheme, has the lowest bias and the lowest group mean square error and the highest or equal highest correlation coefficient for wind and temperature. So that's pretty good news. That's very encouraging. And when we did our global tests, this is the sea ice here for the Northern Hemisphere. And the other 3 plots are the new scheme, the L12E16 scheme, minus the old operational drag scheme, which was this rough scheme. And you can see that the magnitude of the differences here are typically, 2 to 3 up to 2 to 3 meters per second, in terms of near surface wind. with it concentrated in the marginal ice zone, but kind of spread over the whole sea ice area. Temperature differences of up to a couple of degrees, and quite an impact on mean sea level pressure, so up to sort of 1 hectopascal, which was kind of interesting because the Met Office, they were quite pleased with this result because it was pushing their model to their forecast model, their operational forecast model, in a direction that they wanted it to go in, because you know, this is just one part of the drag that the surface imparts on the atmosphere, and this drag change was helping with other aspects of the drag in their model. So to conclude on this sort of first part, we've developed we've calibrated and evaluated a new sea ice drag parameterization that has a significant impact on the atmospheric boundary layer. We used aircraft observations to show that the new scheme had the lowest bias and lowest root mean square errors in some model sensitivity tests. Sorry, that was my phone. And in global simulations, we showed that the atmospheric response is relatively widespread, impacting most of the Arctic and Antarctic, and it had a critical impact on atmospheric drag. And so this convinced the Met Office to put this into their operational configuration from September 2018, and it's also gone into their climate model. So it's going to be in the next set of climate simulations. And there's more about that in this paper published a couple of years ago in Quarterly Journal. So that's sort of part one, which is looking at atmosphere surface drag or momentum fluxes. But I was also asked to talk a little bit about heat and moisture fluxes, and this is more recent work. So I've got a nice sketch here of what's going on. So again, this is the marginal ice zone here. We've got, it's again a cold air outbreak situation, so winds coming off the sea ice pack over the marginal ice zone where there's a lot of turbulence, and so some deceleration, and then speeding up a little bit again when you get over the relatively warm water. And you can see that in this situation, you're going to get changes in the heat fluxes here, which I've indicated by the length of these red wiggly arrows here. Let me just switch my laser pointer on. That doesn't matter. So you can see that over the sea ice, we've got pretty small amounts of heat and moisture fluxes. But as you move through the marginal ice zone, these pick up because you've got some open water areas, you know, some leads and polynyas. And you typically get a peak in the heat fluxes just off the ice edge when you've got the coldest air and you've got no insulation from the sea ice. But the exact functional form here of the heat and moisture exchange across the marginal ice zone is not very well known, and not very well quantified, and the way it's dealt with in numerical models is relatively primitive at the moment. So this is a little complicated, but we'll just try and focus on thinking about the exchange coefficients. So in the same way that we have an exchange coefficient for momentum, which is part of the parameterization of the way that drag is imparted, or the way that momentum fluxes are exchanged between the atmosphere and the surface, we have the same sort of exchange coefficient for heat, and that's proportional to the heat, or equivalently moisture fluxes that are exchanged between the atmosphere and the surface. So in the marginal ice zone, this is often, well, in the MET-UM, for example, it's represented as, again, a proportion related to open water fraction, and then an exchange coefficient over ice related to the ice fraction. So CHN ice multiplied by the area of ice, and CHN water multiplied by 1 minus the area of ice. And, you know, naturally you would take CHN water from the ocean exchange scheme so that it all fits smoothly with your open water area. And your CHN ice, so the exchange coefficient for heat over ice, well, that would be typically set in these models to be a function of the roughness length for ice and the roughness length for temperature for ice. And then in these two models here, the Met Office model and the ECMWF integrated forecast system model, this is set really simply. So they simply say, okay, we don't really know what Z0 T is over ice, so let's just set it to a constant function of Z0 ice. And in the Met Office, they have a coefficient of 0.2 to weight it here, and in ECMWF, they just have a coefficient of 1. So if you look at these graphs on the right, here are the CDN in solid, and in terms of the exchange coefficients for heat and moisture, it's the dashed lines, green for ECMWF and blue for the Met Office. So you can see it's quite a simple thing. Now, to ask the question then, how does that compare to observations? Well, first of all, we have to look at some observations of drag. And these observations on the left here are from the field campaign that we've just been showing you some data from. This is the Acacia field campaign, same observations. It's a smaller subset actually for technical reasons, but the same observations as the black here, and the model parameterizations are the green and blue lines from the Met Office and from ECMWF. And you can see that broadly speaking, the model does a decent job here if we fix the, especially if we fix the values for the 100% ice box. If we use the operational values, it's not quite so good. So this example on the right here is from the other field campaign I mentioned from 2018. That's the Iceland Greenland Seas Project field campaign. And you can see again, CDN can be represented quite well, especially if we fix the values for this. There's one box here over 100% sea ice. If we use the default values, then we are getting this peak in heat flux in exchange coefficients here, but the value is a little bit low. And that's because for the IGP, the average sea ice was much rougher. So we typically had stronger winds and a much rougher sea ice over this IGP campaign, as you can see from the two photos here. So what does that do for the heat exchange coefficients? Well, you can see that for the Acacia field campaign, CHN is actually matches the observed CHN from the aircraft pretty well. But in contrast, the model parameterized CHN for this IGP campaign is way too high compared to the observed exchange coefficient for heat. And that's basically because of this previous diagram here. The actual exchange coefficient for drag is much higher for that field campaign. And that leads to the model having too much heat exchange. So model schemes overestimate this heat exchange. So why is this heat and moisture exchange so similar in the two data sets, despite the momentum exchange being so different? And I don't want to get into too much detail, but it's basically because of different roughness transitions, roughness profiles, if you like, or regimes. Regimes is the word I'm looking for. So the Acacia data is basically all from this aerodynamically smooth regime where the atmosphere sort of flows over what are relatively small roughness elements. So these blue triangles here are relatively small. Whereas in the IGP campaign, the roughness elements are much larger and you get some mixing, enhanced mixing, and you get flow going, having to sort of dive into between these roughness elements to allow moisture and heat exchange to take place. And there's some theory by Ed Andreas, who I'm sure many of you know and remember, and he looked at this for over ice and snow surfaces and did some theory here and found that 3 different transitional regimes were popped out of the theory. So the smooth, the transitional regime, and the rough regime. And when we looked at that in our observations here, so this is the same diagram. So I'm plotting Z0 T over Z0 against roughness Reynolds number, which is just a measure of just a measure of aerodynamic roughness. So this is the same diagram as shown here from Ed's paper. And you can see that our observations quite naturally fall into these 3 different regimes. In the smooth regime, aerodynamically smooth regime, there's not much change in our observations, and they match the model parameterizations quite well. But as we move through the transition and into the rough, aerodynamically rough regime, you can see that the observations drop right off. This is a log scale here, so they're changing by orders of magnitude here. And that broadly follows the theory of Ed Andreas's work, both for temperature and for moisture. And you can see that the models don't follow this because they'll have this constant coefficient, this constant K. So we've come up with a remedy for this. We've come up with a sort of a new parameterization for the marginal ice zone, which blends together the Andreas scheme for sea ice with a different scheme for surface exchange over sea. And when we do that, we get these purple lines here, sorry, magenta lines here. So I've plotted the magenta line for heat here for the Acacia data, and you can see that that matches quite well. In fact, all the schemes match okay for the Acacia data. But in this much rougher IGP data set, you can see that the blended scheme, where we blend the Andreas data in, matches the observations in a pretty reasonable way, whereas the existing model schemes, the blue and the green, really have too much exchange coefficient for this particular field campaign and this data set. So, and this has a knock-on effect in the heat fluxes. So these are just scatter plots of heat fluxes from this IGP data only. And you can see with the blended scheme, you get a pretty good correspondence between the observed flux and the parameterized flux. I just should say that these are offline calculations. This is not from a model. These are just offline calculations using the 3 different bulk flux schemes. And whereas the Met Office and ECMWF algorithms have quite a high bias, as you can see from these scatter plots. So to conclude, on that second part, I have gone through that quite rapidly and it is quite technical, but I wanted to keep the talk to sort of 20 minutes. So, so heat and moisture exchange over the marginal sea ice depends on aerodynamic roughness, both the surface roughness and the wind speed, and this varies significantly with region and conditions. Current model schemes don't take that into account. They just have a proportion of the Z0 ice, and this is not appropriate for different, especially for the aerodynamically rough regime where you have a lot of vertical faces, so a lot of drag in the marginal ice zone, for example, or where you have really rough sea ice. So we've proposed a solution which is was in the magenta, the coloring here, which incorporates this theoretical ideas, this conceptual model from Ed Andreas. And we've proposed turning that conceptual model into a parameterization scheme, which allows for both the smooth and the aerodynamically rough regimes. And we've tested that in offline calculations, and it seems to correspond much better. And this work is currently under review, JGR atmospheres. And we do have plans then to test this in some NWP models, but there are, of course, other obstacles to this working well. So thanks very much for your attention. A little bit over 20 minutes, but not too bad. I'll just stop sharing.
Great. Thank you, Ian. Thank you for speaking on behalf of your colleague who's on vacation. So we really appreciate that. I'm going to pass the torch over to Wilbert, who is a collaboration team lead for physical oceanography team, and he will help me go over the question and answer session.
Great. Thanks, Ian. Thanks, Drew. Thanks, Ian and Maddie, for the very, very interesting presentations. I think this is a really nice example of a collaborative session for the IRPIC collaboration teams. So yeah, with that, we'll open it up for questions. I'm not sure if people can raise their hand, but if you have a question, you can put it in the chat, or if you can put in the chat that you're interested to ask a question, then we can call on you and you can ask your question. So while you're doing that, I would like to ask Ian to tell a little bit about the observational campaigns that he's been involved in. We had a nice chat at the AMS Polar talking about the Greenland-Iceland project, for instance. I was wondering if you could give us this community an update on those projects that they might not be very familiar with.
Sure. So I guess the work we've done, or I've been most involved in, has been aircraft-based meteorology, where we've used, for example, a twin otter, which is able to fly quite low. So within the atmospheric surface layer, we're typically flying 30 to 70 meters above this, well, above the sea surface, and in fact, sometimes down to 15, 20 meters above the sea surface, which is very exciting, of course, a lot of fun. And when you do that, you're able to fly in the surface layer and measure turbulence on particular legs. So you might fly, for example, a 100-kilometer leg across the marginal ice zone, and then divide that leg up into, for example, 10-kilometer runs, where you hope that each of those runs is relatively homogeneous. So you would hope that you'd be flying across 10 kilometers where the ice fraction was roughly, say, 50%. But of course, that is challenging, of course, because the properties tend to be changing. But that's what we did to get these data sets. So in both of these field campaigns, we started with perhaps 200 data points, so 200 sets of 10-kilometer runs. But quality control and making sure that the surface was relatively homogeneous, we'd often end up with more like 100 to 150 data points, because you'd lose some of those data points with the quality control. But those aircraft-based data are a good way of observing the marginal ice zone, and of course complement ship-based observations like we saw from Maddie's talk. And indeed, I've got another project with Ian Brooks, who from University of Leeds, who some of you may know, looking at these sorts of air-sea interaction over marginal ice zone problems with some ship-based data. And we've got a study which we're getting ready for submission using a big ship-based data as well, which obviously having two different platforms allows you to sort of complement and corroborate the results.
Great. Thanks very much, Ian. John, you want to unmute yourself and ask your question?
Sure. Thank you, both of you, for your nice talks. I noticed, maybe I misheard, but it seemed like there was a bit of a discrepancy that Maddie was saying that particularly in the pancake ice situations, the drag went down, and yet Ian talks about in the marginal ice zone, the drag goes up. So does there have to be some consideration about the type of ice in the marginal ice zone to figure out what the drag really is?
Do you want to go first, Maddie?
Yeah, I mean, maybe you have more to say about it, but yeah, I mean, I think pancake ice is definitely a kind of unique case, and it does have lower drag, and so I think there probably does need to be consideration for ice type. I mean, it can often look like 100% cover, but it's this sort of like loose, frazzly, very smooth, and definitely has different drag characteristics than a similar concentration of like brash ice or kind of old broken flows. So
Messy.
I think it's partly explained by the different regimes that you saw in the figures from our two talks. So if you think back to my talk, then the ice tended to be older. We were flying at the end of winter in springtime, and so you had ice that was typically somewhat rafted together and with snow on and vertical faces. And the movies and images that Maddie showed were, I think, more like late summer and with a lot of brash ice, and as she says, which is going to damp down the waves. So I think in my talk, I didn't really talk about the impact of waves, but it will certainly have an impact. And I guess future work should really be looking at both the aerodynamic roughness changes and the wave changes as well, because and neither of these things are in the current generation of NWP or climate models. So we're making some small progress in adding in some of these aerodynamic roughness elements, but the waves element also needs consideration.
Thank you.
Are there any more questions? I don't see anything in the chat. I don't see any hands raised. So I guess I have a little bit of a more philosophical question, and it's just reflecting my ignorance, I suppose, and maybe for Maddie. She showed the energy input by the winds was kind of is dissipated locally, right? So what is the consequences of that for driving the large scale ocean circulation by the winds, if the energy that is kind of locally dissipated in the mixed layer?
It's a good question. I'm not sure I have like a great answer off the top of my head. I mean, we do see this kind of gradient in the energy input across the marginal ice zone, and that's certainly going to have consequences for how the ice is moving and the kind of large scale circulations. And I think we can see kind of some evidence of that on, I mean, in some degree in the like kind of satellite scale. Sometimes you can see these gradients along the marginal ice zone edge. Yeah, I'm not sure what to add. I mean, I think that there's a lot. There's kind of different scales at which this kind of impact accumulates. And on the fine scale, we can definitely see the impact from just a small amount of ice up into the pack ice. And that'll certainly have consequences on the large scale.
You can look at the analyses like Carl Winch and Raf Ferrari have done on the energetics of the ocean, and a lot of the wind energy is dissipated in the surface mix layer. Then there's a small fraction that goes into wind work on geostrophic flows, wind work on internal waves, near inertial motions. But a lot of that energy, as you say, is locally dissipated right in the surface mix layer.
Right. Yeah, it's cool work. Thank you. Are there any more questions or hands raised? Well, if not, then maybe we should conclude the session. And Drew, you want to take it over again?
Yes, I will. Thank you so much, Wilbert, for taking over the question and answer session. So thanks everyone for joining. This is recorded and we will upload this on our YouTube channel as well as this event page within a couple of days. So thank you everyone for coming. Thank you very much to both Maddie and Ian for joining and for giving their fantastic talks. We'll see everyone next month.
Thank you.
Thanks, everybody. Bye-bye.
Thank you.
Thanks again.